Okay, so let's get started. Picking up where we left off yesterday in section 10.3, which is about the definite integral. And as we talked last time, the definite integral is the idea behind, whoops, wrong thing. Definite integral is where you are given a beginning and an end for the integration. You're still integrating the rate of change function, which is the derivative, and what you're going to get by integrating the rate of change from A to B is you're going to get the value of the actual function that you have the rate of change for, from a beginning value to some ending value. And it turns out that number that you get at the end is basically the area under the curve, which is the total amount of change, not the rate of change, but the amount of change from some beginning value to some ending value for whatever that function is. And I said in English, basically the way you calculate it is by finding the sum of the areas of a bunch of rectangles, n meaning a bunch of, as n approaches infinity, which gets back to the ideas from chapter 11 about approaching infinity. Let your rectangles now approach your increments. A rectangle is an increment now. And as the number of rectangles increases without bound on an interval from A to B, then the tops of those rectangles more and more and more mimic the actual value of that rate of change function. And the one that we looked at last time in some detail was a quarter of a circle that has the expression square root 4 minus x squared as its equation. And we know how to find the exact area of that quarter of a circle because it's pi times the radius squared. So the radius of the total circle is going to be pi times 2 squared, which is 4. So if the total area is 4 pi, then the area that we're seeing here is pi. And we checked and saw that we could approximate that area, but not very well, by using two rectangles, 1 unit wide and square root of 4 minus x squared tall. And if we set those rectangles to where the first one had its left edge against the x-axis, we saw that those two rectangles overestimated. And then we saw that if we tried to do it with two rectangles where the right edge actually is the one that's being estimated, then we don't even have enough room to have a right edge on a second rectangle, so it was drastically underestimating. If we tried to put the rectangles in the middle, that worked somewhat better. It worked better than either of the other two because the overestimations and underestimations tended to cancel each other out. If we broke it up into 4 rectangles, it didn't much matter whether we aligned them to the left or to the right or in the center. What we found out by doing it several different ways was that if you had more rectangles, regardless of whether they were what we call left rectangles or right rectangles, or even if we used a trapezoid, which is a rectangle with a piece of triangle on top of it, or we use midpoint rectangles, we got the best approximation that we were likely going to get either by doing 50 of the midpoint rectangles, 100 made it a little bit better, and 500 made it almost perfect. But that's a lot of rectangles, and we get tired of the saying base times height 100 times and doing the arithmetic 100 times. So we know that's what the exact area is, and then we generalized and said, well, you know what, if you have any kind of a curve, and let's face it, we don't have a formula for that curve. If you have any kind of a curve, basically the best way to approximate the area under the curve is to make more and more and more of the rectangles, except for the fact that the process is very tedious to try to find the area that way. It takes a lot more arithmetic. So the last thing that we're going to look at is, this is a general idea of what happens. The more of these rectangles you make, the better the approximation to the area. And that's what led us to the definite integral. Now there is one note to make on this, and I said it last time. The indefinite integral, that's where you actually do the formula for integration. And if you have information called an initial value, then you can find the value of the constant. What that gives you, what the indefinite integral, which means you don't have a beginning and ending point, what the indefinite integral actually gives you is a formula, a set of functions. Those functions are functions whose rate of change was integrated to return to us that original function. In this section, what we're talking about is using antiderivatives to find a definite integral, which is the area under a curve. It is not a function, and it is a numerical process. There's going to be a numerical answer, unlike when we had the derivatives. Now, one thing we could do is we can get the exact area of that quarter circle by letting your calculator do what's called numerical integration. So if you've got your calculator, you might want to follow along with me on this. Mine's the old-timey one, but I think we can all find it together. First thing that you're going to want to do, you can graph this function, okay? You can graph it so that you can actually see the area under that curve. If we're going to graph it, you just go to y equals, and you enter in the function that we're integrating, which is the square root of 4 minus x squared. You don't have to put in the integral and the dx right now because we're entering just the rate of change formula. And then, since the window we're most interested in, since we know that circle's only going to have a radius of 2, what I'm going to do is I'm going to choose the zoom window and go to number 4, zoom decimal. And at this point I see the half circle, the complete half circle. But since I only want to see the part of it that's in the first quadrant, once I see the complete half circle, I'm going to go into window and change the minimum x value to 0 and the minimum y value to 0. And we can see an exact picture of that. Okay? Now, if I go back to my home screen and I want to calculate that area, then just like you found inderiv on your math menu, you also find function integral on your math menu. So you press your math button, and you go to number 9, the option after inderiv. So chances are wherever you found inderiv is where you're going to find FNINT, which is the definite integral of the function. So you select the definite integral, and mine isn't going to show you the pretty form. Mine, I have to know what order to put things in, but it's the same order as we did for doing integration, or for doing derivatives. We have to start out with the function itself, and we need to know what the limits of the integration are. So what we're actually integrating is going to be from 0 to 2. So my function is in y1. Now yours may ask you this in a different order because it just depends on which one it is. So my function is in y1. I'm going to begin at 0. I'm going to end at 2. And my derivative is with respect to x. So there's your dx. Now I may be backwards on how to put those in, so be patient with me a second. Yeah, I put them in the wrong order. So you enter your constants first, I think. Let's see if this does it. Okay, be crabby. Okay, the limits go at the end. I should have just went ahead one. Okay, so we do function integral, and we do like we did before, we're going to start at the function. And rather than go to y1, you can enter in the function itself, so I can do that too. And the derivative was taken with respect to x, so the only thing that we're adding at this point is what's called the limits of the integration, the beginning and the ending. And it thinks and it thinks and it thinks, and it comes back and says, oh, that's 3.141593074. And you know that the value of pi, which your calculator will also show you, is really, really close to that. The difference doesn't occur until the 1, 2, 3, 4, 5, 6 decimal place. So the difference is very, very, very small. Okay? But it is a numerical integral, whereas this is actually an exact number, or as exact as the calculator can show you. So, for example, and this is a different one, and I'm going to show you a couple of things about this one. This is finding the integral of 2x dx. And I'm not going to do a lot of the rectangle method. I'm going to maybe do a little bit of it, but then we're going to go on to the next section. So if it's 2x is my derivative, when I graph that, what's that going to look like? What's y equals 2x look like? Is it a curve? No, it's linear. It's a linear function with a positive slope, and its slope is 2. So if I want to integrate that from 0 to 4, then basically my window is starting at 0 and it's going to 4, so I should be okay. I may need to increase the y a little bit. I'll have to wait and see. But I should be okay. So let me just graph that. Okay, now I can't see the value at 2, so I'm going to raise the window up just a little bit. So I'm going to multiply that 3.1 times 2. And then to find out what the value of that function is at 2, I could get the calculator to tell me, but since it's 2x, what's 2 times 2? 4, okay? So let's do this. Let's talk geometry side, and then we'll talk calculus side. Here I've got a graph. This is 0, 0. This is 1, 2, 3. 1, 2, 3, 4. Right there's the point, 2, 4. And even though I could plot points all the way, the rest of it, I know it's a straight line that goes through 0, 0, and 2, 4. So I'll just draw that line. Now, even though we know this function goes on, it continues on upward in that fashion. The part that we're interested in is only the part from 0 to 2. And if the part that I'm interested in is only that part that I just shaded in green, and I'm trying to find that area without calculus, because this one I can find easily enough without calculus, the formula for finding the area of a triangle, the exact area, formula for finding the area of a triangle is equal to 1/2 times its base times its height. Well, its base is 2 units. And its height is 4 units. So its exact area is 4 square units. Whatever units it's being measured in. So we know the exact answer. Now we could talk about approximating all day long. There's 2 or 3 different ways we could approximate it. We could approximate it still using geometry formulas by finding the area of the first triangle there, which would have a height of 2, and then we could find the area of this rectangle, which is 1 unit wide and 2 units tall, and then the area of another rectangle that's 1 unit wide and 2 more units tall, which seems like an awful lot of work to go to when we have the total area anyway. But this is basically what calculus does, is it breaks up this area into smaller areas. That's what the definite interval does. So if we actually try to find this same problem just using the calculator with numerical integration, it tells us the area is 4. Now that's the calculator answer. We can also do this very, very easily with calculus. using your anti-differentiation formulas. This is the integral from 0 to 2, and this is how you tell a definite integral from an indefinite integral, because it has numbers at the top and the bottom of it. So that's the definite integral from 0 to 2 of 2x dx. This one isn't a hard one to actually find the integral of. We're still doing the integral from 0 to 2. We're going to move this 2 outside and take the integral of x dx, remembering that the power on that x is 1. So that's 2, and the integral of x dx is x to the 1 plus 1 divided by 2. And then the way we're going to indicate that we're going to actually evaluate it and make it a definite integral is we put just a long line rather than being all swirly and make a curved line, and we're saying we're going from 0 to 2. So that is equal to, let's see, these 2's cancel, and 1 plus 1 is 2, so that's x squared evaluated at 0 and 2, and then we subtract. So that's 0 squared minus 2 squared, which is equal to 0. I'm sorry, I did that backwards. You go from the top to the bottom, not the bottom to the top. So it's 2 squared, sorry, minus 0 squared. Let's just rewrite that. So 2 squared is 4 and 0 squared is 0. So this integral is actually equal to 4. Okay? That's actually doing all the calculus by hand. And the answer we get, once again, is exactly the same as the exact area, which we could get also using the calculator. So here's the good thing. Definite integrals can be checked using function integral on your calculator. But even if we don't, since you know how to take an antiderivative, all you're going to do is take what you get from your antiderivative and plug in the endpoints of your integral and subtract your answer. Now there are some finer points we're going to have to come up to in that. Some of the examples will be a little more complicated because some of the area may not fall above the x-axis. You're also going to have to be careful that you don't do what I just about messed up and did and do the integral backwards, so you don't start here and end here. When you do your subtraction, you take the final minus the initial, because that's the total amount of change. So let's try another example. Here's one that's more going to have to be done with geometry. So we're going to use the calculator to help us do some arithmetic. This figure shows that oil is leaking from a machine in a large factory in cubic centimeters per hour with specific rates over a 12-hour period given in the table. And what we want is to approximate the total amount of oil that leaks out of that machine over a 12-hour shift. So notice at the beginning of the shift here, the oil's leaking faster and faster and faster, but it just about stops shortly before 2 hours. It kind of maxes out. And then from there on, it starts not leaking as fast. Its rate of change, the leak is actually going to become slower and slower and slower, so it becomes negative. And at about 5 hours, it kind of bottoms out again. But then it starts leaking faster again, and it leaks at a faster and faster and faster rate until about 8 hours into the shift. And then at 8 hours into the shift, it starts slowing down with the leakage bottoms out at about, not quite 11 hours, more like 10 and a half, and then reaches a peak again at about 11 and a half hours, and then starts to drop off with the leakage again. Now, if you think through this, let's think common sense. This is the beginning of the shift. Let's suppose that beginning of that shift is 6 o'clock in the morning, just to make things easy, okay? So that means from the time the shift starts until about, let's see, 6, 7, till about 7:30, it leaks quite a bit. And then its leaking slows down. What could have happened at 7:30 maybe that the leaking slowed down for a little bit? Stopped using the machine, maybe they took a bathroom break, went to get a drink of water. So if they took a break, then the machine doesn't leak for a while. Now obviously they didn't take a break until 10 o'clock, one would hope. But maybe the machine was running slower, okay? So the rate of leakage slows down. It doesn't completely stop, but it does kind of level out, leaking at a steady rate of pace at about 5.5 hours in, and then it starts leaking again. So maybe what was happening from 7:30 in the morning until about 10:30 in the morning was they didn't have very much work to do. The machine would leak, but they were only doing maybe 1 or 2 parts per hour. Because the machine's running less, then the leak is less. Doesn't mean it stopped leaking, but it's not leaking as fast. And then what happens at, let's see, that's about 10:30. What happens at about 10:30? They get a whole new bunch of parts in that they need to start working with. So they have to start running the machine faster. So the oil starts leaking out faster and faster and faster. Until about, let's see, 6 plus 8, until about 2 o'clock in the afternoon, and then it slows down a little bit. So maybe at about 2 o'clock in the afternoon, they took another bathroom break, okay, and came back and didn't have very many parts left. So it was running very slowly. And then from 6 in the morning until 10 hours, that would be shift change. What's going to be happening during shift change? Machine's probably not, it may be idling, maybe leaking a little and then slowing down and leaking a little. But probably at shift change, the machine is not running at the lowest pace, but it's probably also not running at the highest pace. The person leaving is slowing down. The person coming in is trying to pick up speed. So if you think about it, that rate of change graph makes some sense. But the bottom line for the company is, okay, how much oil do I need to plan on putting back in that machine? How much oil do I have to report to the EPA? That's management's concern. Well, since we don't have the function, the only way to evaluate this is not with calculus. Since all we've got is the graph, our graph is broken up in 1 hour increments for a total of 12 hours. So the actual area of that first bar, which is an approximation of the total amount of oil leak that first hour, is 15.2. You can tell that because it starts just a little tiny bit above 15. And that graph on the oil leak is incremented in 5s. The second rectangle here is a little bit taller. It goes up to about 18 cc's per hour. The third one is taller still. It goes up to 18.8. The fourth one, let's see, those 1, 2, 3. The fourth one drops back down some to about 14.1 cc's per hour. And then for the next 2 hours, it's around 9.5 and 9.6 cc's per hour because the machine's probably idling. And then it starts to climb again, and as it climbs, the height of the rectangles gets higher and higher and peaks out at around 8 hours into the shift, which makes sense. That's about time the shift ends. And then it drops off. So over the last 2 hours, if you assume this person took a lunch break, then their shift probably ended at the 9th hour. Okay? And then the last 3 bars are 19.2, 16.6, 16.4. So it's slowed down some again. In order to find the total amount of oil that leaked, we would have to add up the areas of all those rectangles, which would lead to the not terribly difficult calculation of 1 times 15.2 plus 1 times 18.0 plus 1 times 18.8. In other words, really what we're doing is we're adding up the heights of all those rectangles because they're 1 unit wide. So during that time, 187.8 cubic centimeters of oil leaked out of that machine. Now we could write that as an integral, but we don't have the formula for the rate of change. So while we write it as the rate of change, we don't know what f of x is. But here's one where we could figure out some things. Driver traveling on a business trip checks his speedometer every hour, and the table shows the driver's velocity at several different times. Approximate the total distance traveled during the 3-hour period using the left endpoint of each interval, and then the right endpoint. Now, I'm not going to make you do problems like this. I may, in fact, go in and actually excuse you from 10.3 because I'm more interested in that you do 10.4. But 10.3 is not a hard section to do. Using the left endpoints, they start at 0, and they're beginning at 0 velocity, but they've traveled 52 miles. They're traveling at 52 miles an hour after 1 hour. So they traveled at 0 velocity times 1 because you measured that at the beginning. So at the beginning of the 2nd hour, they're 52 miles an hour for another hour, then 58 miles an hour for another hour, and that's about 110. If you measure those at the right endpoints, then the first rectangle is 52 times 1, the second one is 58 times 1, and the third one is 60 times 1, and it looks like they traveled 170 miles an hour. And obviously both of those can't be right, but the best approximation is whatever is halfway between 110 and 170. And halfway between 110 and 170 is 140. So it's the best estimate of the time that they've traveled. So at this point we need to talk about something called the fundamental theorem of calculus, but I'm not going to make you memorize it. I'm not going to expect you to explain it to me. I want you to know how you can use it. This basically is an explanation of how to calculate a definite integral. This says if you have a derivative, if you integrate that derivative from point A to point B, then what you do is you use your antiderivative formulas, your integration formulas, to find out what big F of x is. And then once you get that formula, including the constant, then you plug in the value of A and you plug in the value of B and you subtract. And that will give you the total area represented by big F of x, which is the area under the curve, little f of x, between A and B. And it's important to notice that it doesn't require that that derivative formula necessarily be positive. It can be negative. You can have a negative rate of change. So let's look at our first problem. What we're going to find is the integral of 4t to the third dt. And then we're going to use what we get to find the integral from 1 to 2 of that same integral. Okay? Here we've got 4t to the third. How would you take the antiderivative of 4t to the third? What is yours? Okay, use the power rule on the 3. So that's going to be 4t to the 3 plus 1 is 4 over 4. Okay? And then the 4's are going to cancel. And you have a constant of integration at the end if it's a definite integral. But we've already seen that this function is the same function, it's only differing by a constant. And if we're going to have that same constant used when we evaluated at 1 and when we evaluated at 2, we're going to take 2 to the 4th plus the constant minus 1 to the 4th plus the constant. It's going to look like this. So you subtract this one from that one. Now remember, you're subtracting the whole thing. What is 2 to the 4th? 16? 16 plus a constant minus 1 to the 4th is 1 minus the constant. Because remember, you're subtracting that whole thing. So what happened to your constant? It canceled out. So even though we recognize that that constant's there, when we do the definite integral, the constant doesn't matter. It's going to cancel itself out anyway. So we can kind of forget about it when we actually have numbers to place into those function formulas. So the integral from 1 to 2 of 4t cubed dt is 16 minus 1, which is 15. Okay? That's the value of the definite integral. And it's 15 square somethings. We don't have a context for it. I don't know if it's going to show it to me or not. I was hoping it would. The newer ones it does. I don't think this one has enough memory to do it. What the newer ones will do is it'll actually show you a graph of 4t to the third on that interval and shade the area under the curve so that you can see it. This one can't do it, it ran out of memory. But it can calculate it really quick. Okay? Now, I'm not gonna go into the whole limit ideas behind the fundamental theorem because that's like revisiting chapter 11, and at this point, we don't really need to spend a lot of time dealing with that. But here are some properties, and I will give you these properties on the exam. This one, the first one says that the integral from a to b of some constant times a function, just take the constant and multiply it times the integral of function. Hold it out front. If it's a difference or sum of different functions, then do each piece separately. If it's an integral of f of x dx, but it begins and it ends both at a, well, if it begins at a and it ends at a, are you going to get any area? The answer is no. You have a line, and a line has no area. That area of a line is 0. So that's why the integral of function, if your two limits of integration are equal to each other, there's no point in doing the problem. Just say it's 0 and go on. Sometimes, we're going to look at an example like this. Sometimes you need the integral from a to b, but you're going to have to break it up and go from some point c that's between a and b. And the reason that we're going to want to do that is because maybe from a to some point between a and b that we'll call c, the function dips under the x-axis, and therefore its area is considered to be negative. And then from c on to b, it's above the x-axis and it's positive. And if you just simply integrate it from one end to the other end, you're not going to get the total area. You're going to get a wrong answer because it's going to add the areas together. So we'll look at an example like that. And then it says that if you integrate backwards, if you're supposed to go from a to b, which means you subtract the function at b from minus the function at a. If you do that backwards and do the function at a minus the function at b, you're going to get the negative of the answer that you're supposed to get. It's just going to change the sign. It's like saying if I was going to do an integration from a to b, but I start at b, I'm going backwards. And if you go backwards, calculus thinks that's negative. So here's an illustration that might be like that. Maybe a is a negative number. So if a is a negative number, sometimes that causes areas to be a little bit funky. If you try to go from a negative number to a positive number, what you need to understand is that the total area under the curve is all of this half plus all of that half. So it has to be done correctly. And this is, I don't think this one comes up in this one, but let's graph it and see, because it may. The safest thing to do is to graph what you're going to integrate before you integrate it. And since it wants us to go from 2 to 5, see, 2 times 4.7 is 9.4. That'll give us plenty of room. But I have no idea how tall it needs to go, so let's just let the calculator figure that out. Okay, so the area we're looking at is something like that. That's about the best picture of it. So we don't have it dipping below the x-axis or anything. We can straightforwardly just do the integral. So the integral, you write it down first. 6x squared minus 3x plus 5 that's going to be dx. We're going from 2 to 5, which means actually the integral we're going to do is from 2 to 5, one term at a time. So the first one is going to be 6 times x to the third over 3 minus 3 x squared over 2 plus 5x over 1, and we're going to evaluate that integral from 2 to 5. So 3 goes in 6 2 times. We have 2x to the third minus 3 over 2 x squared plus 5x, and we're going to evaluate that at 2 and at 5 and subtract. So 2 times 5 to the third minus 3 halves times 5 squared plus 5 times 5 minus 2 times 2 to the third minus 3 halves times 2 squared plus 5 times 2 2 times 125 minus 3 times 25 over 2 plus 25 minus 2 times 8 is going to be 16 minus 3 times 4 is going to be 12 when we multiply it out plus 10. So that's going to be 250 minus 75 over 2 plus 25 minus 16 minus 12 over 2, which is 6, plus 10. That's going to be 10 plus 10, which is 20. This is going to be 250, 275. Which is 312.5. So 312.5 minus 20 should give us 292.5. So everything after the first step is just arithmetic. And we can check that. Give me a different answer. What did I do wrong? Squared minus 3x. I guess it's a good idea to check it on your calculator, huh? Let's try this. Okay, fine. Left something else, sorry. That doesn't look right either, so I have messed up somewhere. I think it's time to call it a day, and I will come back to that one and figure out what I did wrong, because I know the calculator did it right, and I messed up something. So we'll come back and look at that one again. Y'all have a good weekend. I will see you on Tuesday. We will finish, this is 5-4, and, or, I'm sorry, 15-4 and 15-5.
So none of this stuff for chapter 15 Chevy's on there, the homework's on there,
I
right?
haven't posted any of it yet. If I post anything, it's probably gonna be 1 or 2 problems for each section, but I may just let you do my math lab for this one.
Okay, so we're doing all solid, or you're not shortening or anything, it's just doing Pearson, right? Just to go ahead and start doing Pearson.
Yeah, go ahead and start doing the Pearson, get the Pearson done. And the one thing I will do that I haven't decided up until now is I will probably drop 1 homework grade and 1 quiz grade.
So
That way we'll drop the lowest grade.
these quizzes are required.
The end of the chapter review quizzes, where there are quizzes, there's not quizzes for all of them. Some of them I didn't make.
So it's like chapter 11 review quiz, and there's like one that like you're gonna check every chapter.
Except chapter 13, 14. 13, 14, we did a quiz together.
Right. So those review quizzes are required, they're part of the quiz.
That's part of your quiz average.
Tuesday, I have to take the exit exam,
Okay.
and we only have a couple of times. And so you said you were gonna have a test Thursday.
I'm gonna give you the code to take the test online on Thursday and give you the rest of the week to take it. But once you've taken it, you have to bring me your pencil and paperwork so that I can give you partial credit. That way, when you do the test in my math lab, you can actually see your answers. I'll set it up where you can go ahead and see how you did and see which ones you missed. But the thing is, it doesn't always do it right. It counts off things that I would have counted right. So the grade you see will be the lowest possible grade you would make. You're probably gonna make 3 points higher than that. Okay? Yes, please do. I appreciate that. Because after y'all put your forms in, I'm not supposed to hand it out all. Thank you. You too.